This first problem from the E&M practice test was somewhat of a Gauss's law problem, but it's not the typical Gauss's law problem. Normally, with Gauss's law, they give you the charged object and they tell you the charge distribution. And from the charge distribution, you go through and you use Gauss's law to calculate the electric field. And then they usually have you take that electric field and integrate the electric field with respect to position to get the change in voltage. And then sometimes from the change in voltage, they'll ask you something like the work done to move a charge between 2 points, or they'll ask you something about the energy that something gains when it moves off to infinity, or they'll ask you to calculate the capacitance of an object. In this problem, it's a similar type of thing, but it's really asking you to do Gauss's law problems in reverse. They're really seeing if you understood what all of this stuff meant. In this problem, they give you the voltage equations, and from those you're going to come up with the electric field equation and then the charge distribution. So they give you the voltage as a function of R, both inside and outside of a spherically symmetric charge distribution. They give you the net positive charge, and the net positive charge Q0 is distributed within the radius capital R. And they give you the voltage as a function of position. The voltage when R is greater than capital R is just the voltage of a point charge Q0. The other charge distribution is not a constant charge distribution, something that you're going to have to come up with. So for this problem, on the formula sheet that you're given, you have to know that the equation for electric field as it relates to voltage is on there. In fact, this is the equation that you have to use even when you want to find the voltage from the electric field. You have to rearrange that equation into dV equals negative E dR and integrate both sides to get the change in voltage equals the negative integral of E dR. That's a more important equation than this one most of the time, but often that's the way you need to use it. This is the only one that's given on the formula sheet. So for this, I'll go back and I'll answer whether this was radially inward or radially outward at the end. The electric field is going to be the negative derivative with respect to R of the equation that you're given for voltage. So for this first part, I'm looking for R less than capital R. So that would be my first equation there. So it's Q0 over 4 pi epsilon 0 capital R times the quantity negative 2 plus 3 R over capital R squared. And the important thing is recognizing all of the constants that you can pull out. The Q0 over 4 pi epsilon 0 R are all constants, so I don't need to worry about those when I'm taking the derivative. So I have negative Q0 over 4 pi epsilon 0 R times the quantity. The derivative of negative 2 is 0, and the derivative of 3R squared over capital R squared is 6R over capital R squared. So this electric field is negative. That means that it's pointing radially inward. And the magnitude of the electric field, you need to take the absolute value of that. So that's just going to be 6Q0R over 4 pi epsilon 0 capital R cubed. Now the other way that you could have got that the electric field was radially inwards was to look at what the voltage at 0 is And the voltage at 0, at R equals 0, is negative. It's negative 2 times all those constants out front. Q0, 4 pi epsilon 0 R squared. The voltage at R is Q0 over 4 pi epsilon 0 R squared times negative 2 plus 3. So it's positive. This means that the voltage increases. So as you go from 0 to R, the voltage increases. That means that the electric field must be pointing the opposite direction. And the reason for that is E decreases as you move with the voltage. Excuse me. The voltage decreases as you move with the electric field. Knowing that really helps you answer a lot of different problems. Part 2, they want you to find the electric field for R greater than capital R and answer whether it's radially inward or outward. So if I wanted to do it the same way that I did before, the voltage at capital R is positive. It's positive Q0 over 4 pi epsilon 0 capital R. And the voltage at R equals infinity is 0. So the voltage is decreasing as I move away from this object now. So that means that the electric field is pointing away from the object. Again, we'll see that in our electric field equation. The electric field is going to be the negative derivative with respect to R. And if I go back up and I look at my equation, it was Q0 over 4 pi epsilon 0 R. So again, the Q0 over 4 pi epsilon 0 are just constants. And I'm taking the negative derivative with respect to R of 1 over R. So that's negative Q0 over 4 pi epsilon 0. The derivative of negative 1, the derivative of 1 over R is negative 1 over R squared. So it's positive Q0 over 4 pi epsilon 0 R squared. Again, the fact that the electric field is positive means that it's pointing in the positive R direction, which is radially outward. And that is the magnitude of it. It is the absolute value. Again, that equation, E equals minus dV dr, is on the AP formula sheet. You need to make sure that you know all the equations that are on there. Not that you have them memorized, although a lot of them come up in the multiple choice section. But you need to know what's on there and what it would be used for. And this way, if they twist up a problem a little bit, you still know how to go through and solve it. Part B. They want you to figure out the charge, the enclosed charge that generates the electric fields in the different regions. So we have Gauss's law. Gauss's law tells us that the integral of E dot dA equals Q enclosed over epsilon 0. For most Gauss's law problems, that's the very first thing that we do. But that had nothing to do with the first part of the problem. This comes up in the second part. But we need to recognize that this is a spherically symmetric charge distribution. They told us that. And what that means is that the electric field is spherically symmetric. So that means that our Gaussian surface is a sphere of radius r, and our electric field is constant everywhere on the surface of that sphere. So again, if the electric field is perpendicular to the surface of that sphere, which it is, the electric field is radially outwards, and it's constant everywhere on the surface of the sphere, that integral of E dot dA becomes E times 4 pi r squared. The surface area of a sphere is 4 pi r squared. Again, the types of distributions you need to be able to do with Gauss's law are spherical distributions of charge, so spherically symmetric situations. Cylindrically symmetric, so that would be a line of charge, an infinitely long line of charge, or a coaxial cable, or a cylinder with charge on it. And you also need to be able to do a flat sheet with charge, either a conductor or a non-conducting sheet. And this equals Q enclosed over epsilon 0. So from that equation, Q enclosed is going to be epsilon 0 times the electric field times 4 pi r squared. Well, in the previous part, we calculated the electric field for these different regions. So Q enclosed is going to be epsilon 0 times our electric field calculated in part A. But again, I'm looking at R less than capital R. So it's the 6Q0R. And we need to include the negative sign here. The electric field, the magnitude of it was 6Q0R over 4 pi epsilon 0 R cubed. But again, remember we had the negative sign there. The negative sign is important because this is including the fact that the charge distribution has to be a negative charge distribution for the electric field to point inward. Again, if I didn't include that negative sign, I have to realize that my enclosed charge has to be negative because the electric field is radially inward. And I would have to make sure I put that negative sign in at the end. But it does work out, the electric field was negative, so if I include that negative sign that should be there, everything works out fine. And so I have to multiply that by 4 pi r squared. And then looking at this, 4 pi's cancel out, the epsilon zeros cancel out, and I'm left with the enclosed charge is negative 6Q0 times the ratio of little r cubed to capital R cubed. Again, this is not a uniform charge, or this is not the same enclosed charge the whole time. As I get farther and farther away from the center, I have more and more negative charge enclosed. So this is something where it's spread spherically around, and as my Gaussian surface gets bigger and bigger and bigger, but is still inside capital R, it goes through and does this. We had these types of problems where we started with the charge distribution. We were told that negative 6Q0 is spread throughout the whole volume of a non-conducting sphere. And so we figured out the charge density was the total charge over the total volume. And we came up with a charge density like this. And then we had to go through and figure out the enclosed charge when we did Gauss's law. So this is something that we have looked at before, but not as the last step in a problem, but as the first step. If we're looking at R greater than capital R, again, I don't need to go through and write all my Gauss's law stuff. I have the relationship that I need. The enclosed charge is going to equal epsilon 0 times the electric field times 4 pi r squared. So that means that the enclosed charge is epsilon 0 times q0 over 4 pi epsilon 0 r squared times 4 pi r squared. Again, I got that electric field equation from what I had up top. Again, in part A2, that electric field is just kq over r squared. That's just the electric field of a point charge, q0. That's what they say. The sphere has a total charge, q0. And so we should, when we go through and we do this, we should get an enclosed charge of q0. That's something that we should realize as we're doing this. If I look at this, my 4 pi cancels out 4 pi, r squared cancels out r squared, epsilon 0 cancels out epsilon 0, and I get positive q0 as my answer. So there were a few ways of double checking and making sure that you understood this. One of them is realizing that that voltage equation they gave you for R greater than capital R was the voltage of a point charge. Also, that meant that the electric field was the electric field of a point charge, and this enclosed charge has to be the full charge itself. And they said that the sphere had a total net charge of plus q0 on it. So this is what we should get if we enclose the whole thing. Part C, is there any charge on the surface of the sphere? The answer is yes, there is. And the reason why, for R less than capital R, we got that the enclosed charge was negative 6q0 little r cubed over capital R cubed. So at R equals capital R, the enclosed charge is negative 6q0. But when R is bigger than capital R, the enclosed charge is plus q0. So that means that there has to be some charge on the surface that wasn't enclosed when I was right up at the edge. But once I go past the edge, it is enclosed. So that means that the enclosed charge, means that my enclosed charge right at R equals capital R, negative 6q0, plus my charge at the surface equals the total charge of plus q0. So that means that my charge on the surface is positive 7q0. And that was a somewhat tricky question, but it's understanding what those different charge distributions meant. They told you to find the enclosed charge as a function of R, and it's recognizing that things don't quite match up. And that's because there was this charge that was on the surface. It is not enclosed when you're right at the surface, but once you go past the surface, it's enclosed. On the axis below, sketch a graph of the force that would act on a positive test charge in the two regions, R less than capital R and R greater than capital R. Assume that the force directed radially outward is positive. So that's important because our force is in the same direction as the electric field, because this is a positive test charge. So less than capital R, our electric field pointed inward. So that means that our force needs to be radially inward. And if radially outward is positive, then that means that radially inward is going to be negative. And again, looking at the equation that we had on the previous page, it was radially inward and its magnitude was 6q0r over 4 pi epsilon 0 capital R cubed. So this is just some constant times r. So it's a straight line. And again, this electric field, really looking at it this way, this electric field was negative. So I have something that when r equals 0, the electric field was 0, and it gets bigger and bigger and bigger linearly, and it's negative. So that's just going to be some straight line like that. You just make it a different color so we can tell it apart from our axis. And that's what they were looking for that region. And then once we got outside the sphere, the electric field was radially outward. So that means that the force is going to be positive. And the electric field was positive q0 over 4 pi epsilon 0 r squared. Again, it was just kq over r squared, where the enclosed charge was positive q0. So this means that it's going to start at some maximum value, and the graph is proportional to 1 over r squared. So this is something that as r gets bigger and bigger, this approaches 0. And again, it's hard to tell the difference from just a sketch of the difference between 1 over r and 1 over r squared. But again, you should have something that is decreasing like this, approaching 0 as a limit as r goes off to infinity, and it's definitely not increasing or decreasing in a straight line. So just quickly going over the scoring guidelines for this. For the scoring guidelines, it was for part A1, it was 1 point for saying that the electric field points radially inward. And then it was 1 point for correctly substituting the electric potential into the equation for the electric field. Just writing this equation was not enough to get any credit. What you needed to do was show that you realized that what you needed to take the derivative of was the voltage that they gave you. So there wasn't anything else that you had to do for that point. The final point is actually solving it. But if you at least said that you take the derivative of the voltage equation they gave you for r less than capital R, then you get the second point. And then the third point was correctly taking the derivative of the voltage function to determine the magnitude of the electric field. So again, the equation to take the the derivative of v with respect to r was given to you. They gave you v, so you should have realized that you needed to take the derivative of the equation they gave you, and then actually gone through and taken the derivative. But even if you didn't, go through and set it up. If you set it up, and don't just say e equals negative dv dr, if you actually set it up and say what you're taking the derivative of, then you can get some credit. For part 2, it was 1 point for saying that the field was radially outward, and then it was 1 point for correctly taking the derivative of the other function. So they didn't give you a point for setting it up in both part 1 and 2. For this one, they only gave the point for actually correctly taking the derivative. This is a simpler derivative. So again, if all you did is set them up and use them to figure out, and you got the radially inward and outward, you could have gotten 4 of the 5 points. Excuse me, you could have gotten 3 of the 5 points. You wouldn't have gotten the final point for correctly taking the derivative for either one. For part B, for recognizing that you needed to use Gauss's law and writing down Gauss's law, it was 1 point. Again, it said find the enclosed charge, so when it's saying find the enclosed charge, you should realize that you're looking at something with Gauss's law. And then it was 1 point for correctly substituting the expression for flux. So the expression for flux is the electric field times the surface area. And since this is spherically symmetric, our surface area is the surface area of a sphere, 4 pi r squared. And then it's plugging in the value for the electric field consistent with the answer to part A, including that negative sign. That negative sign is important because your enclosed charge must be negative. For part B2, we had that the enclosed charge was given by that same equation. And so it was 1 point for correctly substituting the electric field into the expression. And then it was 1 point for having the positive charge. You found that the field pointed outward, so the charge has to be positive. And again, that worked out if we plugged in all of the correct values for the electric field. Part C, there was charge residing on the surface of the sphere, and the explanation or the calculation for indicating that the total enclosed charge equals the charge at the surface plus all the charge inside the sphere, and the charge inside the surface up to the surface did not equal Q0, so there had to be some charge at the surface. That could have gotten you the point. Just saying, yes, there's charge there, but having an incorrect justification for it would be wrong. A correct justification for it would also be just going through and calculating what that charge is, because in setting it up, you actually are explaining all of that. So the second point for this would be to actually calculate the correct value of 7Q0. Again, the student could earn 1 point for credit for a correct qualitative description of the charge configuration, even if the surface charge was not calculated. But marking yes, there's some charge there, and saying it's a conductor, so the charge is on the surface, or something like that, that is untrue. This is not a conductor because charge is spread throughout the whole volume. So incorrect justifications for why there's a charge on the surface did not earn you any credit for this problem. And then part D, again, this is the graph that I had drawn. And so the first graph needs to be consistent with your answer to part A1. If you said that it was radially outward instead of radially inward, then your force should be positive. If you said that it was radially inward, your force needs to be negative, and then it should have the same shape as whatever function you calculated in part A. And then having a graph for r greater than r consistent with the answer to part A2. And there's a finite value at r equals capital R. That was something some people had it going off to infinity. So you did not get credit, even if your graph looked like a graph of 1 over r squared. If you had it going up to the force being infinitely big at capital R, that would be incorrect. And then the final point was for having a step discontinuity at R equals capital R, indicating the presence of charge at the surface. So the step discontinuity is this part right here, where it goes from some somewhat large negative value up to a positive value immediately. And that's because when you went right up to R, you didn't have that enclosed charge that was on the surface. Then when you go right past R, now you have that enclosed charge. So there's this transition that's happening. Having both of the graphs asymptotic to R equals capital R does not constitute the correct discontinuity. So if you would have had something that approached both of these lines as an asymptote, those would not have counted. You would have not gotten that discontinuity point. Even though that's definitely a discontinuous graph, that would not show the correct discontinuity. It needed to be a specific finite value here and a specific finite value here. Again, the first free response question often is a Gauss's law problem. It often fits into a little bit more standard form than this problem does, but they do try and twist up the question sometimes and really try and probe whether you know it. So their commentary on this was from the chief grader. So many of the major electrostatic concepts were tested. There's an unknown spherical distribution of charge. They give you the voltage inside and outside the sphere. In part A, you're asked to derive the function for the electric field. So it's asking whether or not you understand what E equals negative dV dr actually means. Since the given voltage function was not a simple function, students' ability to correctly take a derivative was also tested. In part B, which assessed students' understanding of Gauss's law, they were asked to use the electric field functions from part A to determine the charge distribution. Again, they were twisting the problem a little bit. It was a slightly different form of this, but it's the same Gauss's law stuff that you do all the time. It's just doing it in reverse. In part C, students were asked about a possible surface charge. The overall charge distribution was a negative charge distributed within the sphere and a positive charge placed on the surface. Students who correctly answered part C demonstrated a very good understanding of Gauss's law. So that part C was the difficult part of the problem. The other parts, while challenging, were things that you easily could have done, or with some time would have been able to think of. C really was, did you really understand it inside and out? In part D, students were asked to graph the resulting electric force on a positive test charge, and this assessed their understanding of the relationship between electrostatic force and field, as well as the visual understanding of the charge distribution. A correctly drawn graph would clearly show a discontinuity at the surface, which allowed some students to uncover and figure out mathematical or conceptual mistakes that they made in earlier parts of the problem. So how did students perform across the country? The average score was 6.27 out of 15. About 10% earned 12 or higher, and about 27% earned scores of 3 or below. The common student errors or omissions. In part A, the most common mistake was taking the derivative incorrectly. Besides not recognizing that you needed to take the derivative, taking it incorrectly. Since the second region was a familiar function of a point charge, students made fewer mistakes for that region. Another common mistake in part A was getting the direction of the electric field wrong, not knowing how to get that either from the fact that the derivative was negative or from the voltage idea. In part B, most students recognized the need to apply Gauss's law. However, many students did not set up the surface integral correctly. Most common was a failure to recognize that in a spherically symmetric situation, the electric field is constant, and so therefore you can pull the electric field out of the equation and you just have the surface area. You're integrating over the surface area. So these students pursued an actual integral involving the electric field function resulting in a very complex expression and an expression that's incorrect. If you actually tried to integrate your function and you didn't recognize that at a specific value of r, which is what you were looking at, it only has one distinct value, um, you know, that was where they had their problem. They tried to integrate with respect to r instead of integrating over the surface of the Gaussian surface. Part B2 was answered correctly by a majority of students who attempted it. So a lot of times if people didn't know how to do B1, they would just leave B2 blank. The familiarity of the field expression external to the distribution helped them derive the expression for the enclosed charge. And you might not have understood these other parts, but realize that you had a charge Q0. They told you that for the sphere, and so you could have just written that down. It was the most challenging part of this problem for exam takers. Many students stated that there was charge on the surface of the sphere, but they gave answers that indicated a lack of understanding. So incorrect statements were things like the sphere is a conductor and all conductors have all of their charge on the surface. But that's not true because there was definitely charge spread out through the whole region. We calculated the enclosed charge and it was not 0 for r less than capital R. Also saying that the charge distribution function shows that charge exists everywhere on the sphere, including the surface. But that wasn't enough. We're saying that the negative charge inside the sphere induces a positive charge on the sphere. Well, that's not what's happening. In having an induced charge is something that happens when you have a conductor. This was negative charge spread throughout, and then a positive charge that was just placed on the surface. It's not one causing the other one, it's just two separate charges that are placed there. We're saying that the net charge of plus Q0 rests entirely on the surface of the sphere. Since you were told that the net charge of the sphere was Q0, that would not be correct either. These statements indicate a lack of recognition that the potential function given implied the existence of a spherically symmetric and negative charge distribution plus a positive surface charge. So that saying that it's a conductor or any of those things shows that you didn't really understand what was going on. Many students who attempted part D earned 2 out of 3 points. Most students correctly drew graphs of their force-field relationship. So they took their answer from part A and correctly translated that into a graph. And most also drew graphs that were reasonably consistent. A common error was the lack of a field discontinuity at r equals capital R. So what are some things that students should do to improve their performance? What things should they look at? They should look at problems that give practice with differentiation, besides just very simple examples. You should look at the relationships among electrostatic potential, electrostatic field, and the distribution of charge. Again, you need to understand Gauss's law inside and outwards, be able to work it forwards and backwards. And this was asking you to do it in reverse. And you should frequently construct and interpret graphs that represent certain functional relationships. So knowing that the force is the charge times the electric field, you should be able to take your electric field graphs and draw graphs of the force.